Let's talk about the expectation values. So up to now, we mostly talked about quantum mechanics as being probabilistic. Therefore, we have to measure, or I should say we can calculate the probability that something's going to occur, and then we can go out and try and measure it. But we want to do more than just try and figure out what the probability is that is going to occur. What we would like to find out is what is the actual value going to be. So if I make a measurement of the position of some particle, I'd like to know not just the fact that how probable it is that this position is going to be, but what is the most likely, what's the expected value of that position. And so what the definition of an expectation value, so I have some measurement omega, and that's basically summing over all the probabilities occurring for some value omega sub I times the value omega sub I. So it's kind of a weighted average is another way of thinking about the expectation value. You're weighting, so in this case I've got a whole list of probabilities, and so it could be, that you have 10% times omega 1 plus 15% times omega 2 plus 1% times omega 3 ... And so and so now if we use the language of quantum mechanics, then this expectation value of measuring omega, I can write down the probability as the norm of all the possibilities times the basis or the vector state psi squared times omega. And then I can expand that as the projections onto the the states times omega, which we could write out in the language of Schrodinger as psi star omega I times psi omega sub I. So basically I can write these down in terms of wave functions instead of as wave functions instead of projections on states. So in this case, what I can do is remember that the operator omega on some state lowercase omega sub I gives me the eigenvalue times that state back again. So if I was to then write down psi omega sub I, that would be the same thing as saying omega I times psi omega sub I. So that gives me the eigenvalue. So if I go back to my expectation value, now what I have is the sum of this operator operating on a particular state, like so. And since the identity is the sum of the projection operator, I can now write down my expectation value as psi omega operating on psi, like so. So now this is our expectation value. We can now calculate what is the expected value of some variable, position, momentum, energy, time, so forth and so on, by taking that operator, operating it on the state, and then calculating the collapsing the wave function after we have operated on that particular state. Okay, so now let's consider the uncertainty in our measurement. We should be able to calculate that because the standard deviation, which you've been forced to learn in all of your introductory physics classes, is defined as basically the measurement minus the expectation value quantity squared to the 1/2 power. Or, in English, we're comparing each individual measurement, omega, with the average value, the expectation value, omega, squaring it because sometimes you can have plus and minus. If you think of this as kind of like the percent difference or even an error, then, half the time each individual half of the data points should be below the expectation value and give you a negative. Half the data points should be above the expectation value and give a positive. So to get rid of the plus and minus signs, we square it right here. And then to get back to our normal variable, you have to take the square root. So that's the, kind of a 30-second explanation of the standard deviation. It's the comparison between the expectation value and each individual data point. And then you do the square and square root just to get rid of all the plus and minus signs. So I can rewrite this now as the square of the standard deviation is just really the expectation value of my measurement minus its expectation value squared. Like so. But we can clean this up a little bit further. So if we consider discrete states, so we haven't gone into continuous functions yet, but if we have discrete data points, then our standard deviation squared is the sum of the probability of each data point, the value of the data point minus my expectation value quantity squared. If we want to consider continuous, which for the most part we will in quantum mechanics, then the standard deviation squared is the integral of the probability density, the measurement minus the expectation value quantity squared integrated over the variable, like so. Okay. Okay, so let's try and see if we can get an easier formula to use than have to kind of always integrating the this probability and trying to take every data point and subtract off the expectation value. And so if I write this back again as the expectation value, then what I have is psi, and I'm going to change this from omega, lowercase omega, the value, to the actual operator, minus the expectation value, quantity squared, operated on the state, psi. Okay. And then, okay, well, let's work out now this quadratic equation. I would have omega squared minus 2 times the expectation value times omega minus the expectation value quantity squared operating on psi. Okay, and so I can break this up into its pieces. I would have psi omega squared projection on psi minus 2. Expectation value is just a number. It's not an operator. So that comes out front. And then I've got psi omega operating on psi. Sorry, this is a plus up here. So plus the expectation value squared, psi projected onto psi. So this is a normalized set of vectors, and so that is equal to 1, and then psi omega on psi is the expectation value right here, and psi omega squared is taking the expectation value of omega squared. So in the end, what I have is the standard deviation squared is equal to the expectation value of omega squared minus 2 omega expectation value of omega plus the expectation value of omega quantity squared. So omega expectation value of omega times the expectation value of omega is the expectation of omega quantity squared. So I get omega squared, expectation value of omega squared minus 2 expectation value of omega quantity squared plus the expectation value of omega quantity squared. Those two last terms subtract, and we get the standard deviation squared is equal to the expectation value of omega squared minus the expectation value of omega quantity squared. And then I take the square root of both sides, and I get the square root of the expectation value of omega squared minus the expectation value of omega quantity squared. And this is kind of a standard equation for calculating the standard deviation. This isn't, I mean, you can get this not just from quantum mechanics, but you can get this from any class on probability and statistics as well. But we're going to use this one. We're going to use this equation to calculate the uncertainty in things like our position, the uncertainty in the momentum of a particle. And so in order to do that, we need to calculate the expectation value of omega, as well as the expectation value of omega squared. So these are two different things. We can't say that the expectation value of omega squared is equal to the expectation value of omega and then just square the whole thing. So that's wrong. Instead, you're looking at two different measurements. You're looking at the measurement of, let's say that omega is the position. Then what you're looking at is finding the position and finding what the square root of the position is going to be. So you're measuring both the position and you're measuring the square of the position, and then you take those two things, put together, and you can find the uncertainty or the standard deviation of your position from these two expectation values, like so.